Hello again, gentlemen. My name is David and once again I will be speaking for Professor Barker. Tonight's talk is about the ingenuity that various individuals put into the search for a workable television system before the advent of all electronic methods. Here I have shown a photograph of Paul Nipkow, who was born in Prussia in 1860. He conceived of his idea for a scanning disc while still an undergraduate. In my opinion, he can fairly be said to have come up with the seminal idea from which future television development flowed. Luckily, he lived until 1940, having seen his idea for, as he called it, an electric telescope, fully realized. In 1983, the German Post Office issued a commemorative stamp, showing the essential details of a Nipkow disk system. On this stamp, the transmitter is on the left. It seems unlikely at first glance that John L. Baird should have become the first man to demonstrate real television. He was largely unschooled in technology. As a career he at first manufactured the so-called Baird undersock, with some success. He then turned to making various kinds of jam in Trinidad. However, Baird was also interested in technology, primitive though it was in the 1920s. He built a small telephone system to experiment with communications with a friend a few doors away from his parents' house. This piqued his curiosity, and in time he was sufficiently self-taught so that he could seriously consider developing a workable television system. By 1870, the photoelectric properties of selenium had been discovered, and in 1885 Paul Nipkow had patented the scanning disc. In 1895 the neon lamp had been discovered, and by 1918, at least two British companies were producing valves suitable for amplifying the weak signals from his photocells. Thus, most of the essential elements were available for Mr. Baird to produce his television system. The vacuum photo tube was invented in 1875, and was pressed into service by Baird as soon as he could find a reliable and sensitive example. Unfortunately, the photomultiplier tube was not invented until 1930 by Grimm, a Soviet scientist. This would have made Baird's work much easier and would have yielded good results much sooner. Here we see Mr. Baird's original television transmitter. This equipment can still be seen at the Kensington Science Museum in London. Someone who saw Baird's demonstration in 1926 described his equipment as being made out of cardboard and sealing wax. But this does not detract from his accomplishment, particularly in view of his continuing and acute lack of money. It shows what a burning interest, ambition, and a belief in one's abilities can do. This apparatus used lenses where the tiny holes would normally be found in a Nipkow disc. However, while this improved the optical efficiency, it posed severe penalties on the size of the disc. In Baird's example shown here, it necessitated that there be only 16 lines of resolution, otherwise the disc would have had to be roughly 4 feet in diameter, for 32 lines, and the balancing problems would have been enormous, not to mention the danger of one of the lenses flying off the disc. In any event, Baird did succeed, and one of the still existing photos from those early years is of the televised face of his young assistant, who achieved immortality of a sort when Baird asked him to stand in for the ventriloquist's dummy that he normally used for testing the system. In this photo I show the type of television reproducer that Baird used in demonstrations of his equipment. Note the chain drive that allowed for proper framing of the picture once speed synchronization was locked in. I will describe the synchronization process later, since it applies to all mechanical systems. One of the problems of the scanning disc was that to have even a reasonable number of lines, the disc had to be enormous. For example, if the picture is about 3 inches wide and there are to be 60 lines, the disc circumference would have to be 90 inches, so the diameter would have to be almost 3 feet. Several inventors took up the search for a better method. One of these was Leon Theremin, the inventor of the musical instrument named after him. Theremin saw that the size problem could be reduced by the use of a drum of mirrors, such that the picture could be projected onto a screen. These mirrors were ranged around the outside surface of a drum. If each mirror was 1/2 inch square, the diameter of the drum would be about 10 inches, a considerable improvement in size. In this picture are illustrated several types of mirror drums. These could be scaled up to about 100 lines, however, the increased inertia of a large drum made synchronization more critical. Our next inventor was C. Francis Jenkins. He had developed some special optics for the motion picture industry and applied these ideas to the problem of television. His primary contribution was the invention of the prismatic disc for scanning a light beam across a screen. This system requires two discs, one running at high speed for horizontal scanning, and one slow-speed disc for vertical scanning. Obviously this device had a capability for much more than 32 lines of resolution, however, TV transmitters still used NPCow discs for televising films, with a maximum of about 120 lines. Here is a page from Jenkins' patent for the prismatic disc system. This equipment uses the Kerr cell, which I will explain later in this talk, to modulate a light beam, which is then scanned by the two discs to form a raster. Here you see a photograph of the two discs. The one nearer the screen is the high-speed disc, which writes the horizontal lines. The farther one is the frame scanner. I suspect that in the days before precision motor controllers had been developed, and before the era of high-power vacuum tubes, synchronization of these two discs was very difficult. Jenkins also produced a mirror drum system, capable of 100 lines of resolution. It is shown in this photograph. Two helical gears run the two drums so they stay in step. However, synchronizing the system with the transmitter was likely problematic because of the power required to operate the gears and the two drums. In a final nod to the ingenuity of Mr. Jenkins, here is his receiver for up to 128 lines. It uses a rotating drum, with 4 identical rows of scanning holes. Behind the 4 rows of hole is a 4-plate neon lamp. Each lamp plate is switched on by a commutator in sequence. The result is a 4-fold increase in the number of lines. Of course, the rotational speed of the drum must be quadrupled. This brings more problems in synchronization, since at 15 frames per second, the drum must rotate at 3,600 rpm, this probably leading to hunting by the drive motor. The next method of note is the mirror screw. This device allowed up to 240 lines to be displayed by a simple process. It consists of a series of thin mirrors, actually polished metal, arranged in a spiral. A line source of light is successively reflected by the mirrors, so that one revolution of the spiral traces out one complete television raster. Shown in this photo are 3 examples made by a member of the NBTV Club. This person even sells mirror screws to those interested in experimenting with this technology. In this diagram you can see the inner workings of a mirror screw receiver. There is on the left a gas tube giving a line source of light. This is reflected by a plane mirror onto the screw. As each successive mirror reflects the light source, a picture is constructed, which appears to be just in front of the screw. Here is an example of a TV picture reproduced by this type of apparatus. A mirror screw was capable of displaying 180 lines, and if well balanced and provided with good bearings, it was relatively easy to synchronize with the transmitter. The final example I will consider here is the Traub mirror device. This is essentially a mirror drum turned inside out. It was invented by a Hungarian scientist. It consists of a ring of mirrors surrounding a rotating mirror. Its advantages are, firstly, the small rotating mirror needs very little power and is easy to synchronize, and secondly that it can be expanded well beyond 120 lines. In fact, the 1937 issue the British magazine, Television, states that the system was being developed to receive the standard 405-line transmissions. Unfortunately, in 1939 the war put a stop to further development. In the diagram can be seen the ring of mirrors, and the rotating mirror at the center of the ring. Note the double reflection of the light beam. Earlier in this talk I had said I would address the matter of how mechanical television receivers were synchronized with the transmitter. The essential element, originally developed by Baird, is what was called a phonic wheel. It is in fact much like a large gear, with as many teeth as there are lines in the picture. This wheel is constructed of laminations, to reduce eddy currents. Closely spaced to the wheel are two electromagnets. This device works only when the speed of the drive motor is close to the desired value. As shown in the diagram, the two electromagnets were connected in the plate circuit of the video output tube, in series with the display's neon lamp. There is a bypass capacitor on the B+ end of the neon lamp, to avoid the effect of the electromagnet's inductance on the video frequency response. At the same time, sync pulses, at one per line, are passed to the phonic wheel assembly. The effect of these pulses is to speed up or retard the toothed wheel, depending on the speed error. Obviously, the phonic wheel would become less effective with, for example, a set displaying 180 lines because the teeth would necessarily be considerably smaller, or the wheel would have to be much larger, with greater inertia. The last thing that I wanted to discuss is the light valve, or Kerr cell, that was the preferred light modulator for most systems other than those using the Nipkow disc. The cell, of which a photograph is shown here, is basically a parallel plate capacitor, filled with ultrapure nitrobenzene. Nitrobenzene becomes birefringent under certain conditions. Unfortunately, it is also highly toxic. When placed between crossed polarizers, and voltage is applied to the plates, more or less light is passed, depending on the voltage level. This is a high voltage device, requiring several hundred volts for full activation. The accompanying diagram gives a good idea of the arrangement of a television display using a mirror drum and a Kerr cell. In this diagram, the two items marked as prisms are the polarizers, known as Nicol prisms, made from specially prepared crystals of Iceland spar. That's all for tonight. In episode 3, I will discuss the last, best gasp of mechanical television. I will see you again then.